All right, good morning and welcome to section 15.5, applications of double integrals, density, and mass. So today what we're going to do is we're going to talk about how we can apply double integrals to find just a few things, so apply them to a few situations. In the first situation we're going to talk about density. Now suppose the lamina occupies a region D of the xy plane, and its density in units of mass per unit area at a point x, y, and d is given by rho of xy, where rho is a continuous function on d. So we have rho of xy is equal to the limit of delta m divided by delta a, or delta m and delta a are the mass and the area of a small rectangle that contains xy, and the limit is taken as the dimensions of the rectangle approach 0. Now, one thing that you need to know about lamina is going to be, an area, but it's a very, 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 very thin, layer to something. Think about applying, a bit of film on something. It's just a very, very small layer. And so that's what all these regions represent, just a very, very, very thin layer. And we can find the total mass m of our lamina. This is a very similar topic in Calc 1, but it's really never talked about. One things that you can do for for an integral, when you're integrating, usually the integration helps you find the area underneath the curve, and how double integrals help you find the volume underneath the surface. And that's what we've been doing, all through Calc 1. You were just finding the area under the curve, or we're finding the volume underneath a surface. Well, one thing that it also does that I don't know if it was really preached in Calc 1 is that it also helps you find the mass of, if we're talking about just a single integral, so just one integral, that helps you find the mass of a string. And in Calc 3, when you do double integrals, that's going to help you find the mass of a lamina, which is a region, because we have a surface, and it's going to help you find the actual mass of that, very, 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 not very thick, very, very, very small piece of lamina. Right? If we choose a point, so we can choose a point in our region, then the mass of the part of the lamina that occupies R is approximately, and so we're just going to pick a region, is the rho of xy delta A. And so we can just say our mass is the sum of all of our regions together of our function, delta A, and that is just going to be the double integral of rho xy dA. And so if I want to find the mass of, of a piece of lamina, all I have to do is take the double integral of the function of that, and that gives me the total, that gives me the mass. Similarly, if an electric charge is distributed over region D and the charge density in units of charge per unit area is given by sigma xy at a point xy and d, then the total charge q is given by, and so all we have to do if we want to find the total charge is take the double integral of our sigma function dA. And so let's go ahead and do example 1. So electric charge is distributed over the disk x squared plus y squared is less than or equal to 1. So that the charge density of xy is sigma equals the square root of x squared plus y squared. Measure in columns per square meter. Find the total charge on the disk. Alright, so let's go ahead and do this. All we have to do is, if I want to find the the charge density, all I need to do is take the double integral of our region of our function. That's an ugly sigma. And that's all I need to do. So let's go ahead and take the double integral. Let's also look at the region. So I'm going to go ahead and draw the region. I'm going to draw it on the xy plane. And it looks like we have x squared plus y squared is less than or equal to 1. So that's going to be a circle with a radius of 1. And so, again, I'm doing double integral. So I can change this if I wanted to. I can change this to polar coordinates. And yeah, that's definitely what we're going to do, is change this to polar coordinates. All right, so we're finding that region. And so in this case, we're defining it as region. It doesn't really matter. We'll just call it region D. All right, and I'm going to change it to r and theta. And so r is going to be from 0 is less than or equal to r is less than or equal to 1. And theta is it's the full rotation of the circle, so 0 to 2 pi. Right. So I'm going to go ahead and put everything in terms of polar coordinates. So then I'm going to have, remember, theta is always on the outside, so 0 to 2 pi. Then we have our sigma. In this case, our sigma is the square root of x squared plus y squared. If we're doing polar coordinates, though, then it's just going to be the square root of x squared plus y squared is going to be the square root of r squared, which is just going to be r. So r, and then don't forget your r, dr, d theta. Don't forget to put in that extra r, which you would have forgotten just because you had just that r. And like, oh, there's the r. Just been excited that you had an r, and you would have just went. All right, so I'm going to go ahead and break up the integration. 0 to pi d theta. And I'm going to go from 0 to 1 r squared dr. I'm going to integrate theta. 2 pi 0, 1/3, that's an ugly 1/3 r cubed, and going from 0 to 1, and so I'm going to get 2 pi times 1/3, and I'm just going to be left with 2 pi over 3, and measured in columns per square meter, so 2 pi over 3c. Go ahead and highlight that, and we're done. You're going to notice